So we're talking about digestive system PowerPoint slideshow part 1. We're going to continue with the stomach, and this PowerPoint is about stomach physiology. I'd like to start by taking you back to the bottom of page 86 and reviewing the microscopic structures of the stomach and their secretions. So we left off in the last video talking about how the gastric pits have a variety of cells specialized to produce various chemicals. So we know that under parasympathetic control, the vagus nerve will stimulate enteroendocrine cells to produce gastrin. Gastrin's a hormone, and like all hormones, it circulates in the bloodstream. It will target parietal cells to produce hydrochloric acid and intrinsic factor. Now, those parietal cells are also in gastric pits along with those enteroendocrine cells. We need hydrochloric acid because that helps us to lower the pH in the stomach to around 1 or 2. And that acid environment helps us to convert pepsinogen to pepsin. Now, pepsinogen, that gen suffix means to begin or start. That's not the active form of the enzyme. Pepsin is the active form. And pepsin helps us to break down proteins. So protein digestion is chemical digestion. And this is really the first time we've talked about breaking down those proteins. So mechanically, we're going to be churning and grinding the food in our stomach, but chemically, we're going to be using pepsin to break down those proteins. Secondly, you'll notice intrinsic factor is also produced by those parietal cells. It's needed for vitamin B12 absorption in the small intestine. Without it, we are impaired in terms of red blood cell production, and we can develop a condition called pernicious anemia. So if you think about people who have had gastric bypass surgery, that could be a real possible problem for them, is having pernicious anemia. So as an aside here, chief cells also in those gastric pits are the ones producing the pepsinogen. What type of pH is necessary to convert pepsinogen, which is an inactive form, to pepsin, the active form that helps us to break down proteins? Okay, that would be an acid pH, somewhere around 1 or 2. All right, and so how do we keep the stomach from digesting itself? That comes from mucus produced by mucous neck cells and surface cells. They form secretions that help to provide a thick layer, keeping our stomachs from digesting themselves. There is also one additional type of protein digesting enzyme I didn't get a chance to mention in the last video. So I also want to point your attention to Renan, which is on page 86. This is a special type of enzyme that only works in young kids, or for the most part in young kids, and it converts milk proteins into proteins that pepsin can act on. So if you've ever seen cottage cheese, that's kind of how Renan acts on milk proteins in our stomach. It turns it into what looks like a curdled, little blocky shaped structure. So in fact, we do use Renan or something called rennet to help make cheeses. It's actually taken out of the stomachs of young cows. Okay, so just to summarize here what we've talked about so far, we've talked about pepsin helping to break down proteins and Renan helping to make those milk proteins specifically more digestible in the stomach. As we age, we tend to have less Renan. In fact, there's lactose intolerance. We have less Renan, so a lot of people, especially beyond age 3, are going to have difficulty breaking down milks, whether it's proteins or milk sugars. So at the very bottom of page 86, let me draw your attention to the summary of activities in the stomach. Mechanical digestion occurs here. When we talked about muscularis externa, there's actually 2 layers of muscularis externa, a circular layer and a longitudinal layer found in most of our GI organs. But here in the stomach, we have a third lateral layer that helps to massage and break up that food, performing those rhythmic contractions known as peristalsis. There's really little chemical digestion here. What we're mainly looking at is milk protein digestion using Renan and just typical regular protein digestion using pepsin. Notice I have not mentioned any enzymes in the stomach for carb digestion, lipid digestion, or nucleic acid digestion. Really, the only thing we're hydrolyzing or breaking apart into building blocks here is Renan and pepsin. In fact, we don't complete the process here either. We are going to finish breaking down those proteins in the small intestine. Last, there's very little absorption here. It is limited to two things. Well, there's a few more, but mainly things like alcohol and aspirin. Those are the blanks, by the way, for the bottom of page 86. Okay, alcohol and aspirin. A little bit of water can be absorbed here, but most of that is done elsewhere in our system. All right, if you are ready, we're going to flip on over and take a look at page 87. So we've talked a little bit about control of gastric secretion. We know the vagus nerve plays a major role. Does it work for your sympathetic nervous system or your parasympathetic nervous system? That is your parasympathetic nervous system. And we know that gastrin is a major controller of getting the ball rolling with gastric secretions. So what type of cell produces gastrin? That would be an enteroendocrine cell. Okay, so we're going to tie together what we've already talked about, how thinking about food, smelling food, tasting food, all those things can go into stimulating the vagus nerve to promote the release of gastrin from those enteroendocrine cells. And where I'm going to take you now is to talk about 3 phases to gastric secretion. All right, so on your worksheet, page 87, you'll notice there are phases 1, 2, and 3. Hey, sorry, the doorbell rang. I had to run off. I'm back now. So with the first phase of gastric secretion, we're looking at the cephalic reflex. And technically this word means the head reflex, or in other words, what your head is doing to initiate what's going to happen in a few minutes in your stomach. So smelling food, tasting food, talking about food. You know, if I mention that tasty hot pizza out of the oven, or maybe fried chicken and mashed potatoes and gravy, or we talked about dessert, you know, something like hot chocolate cake with some ice cream on it. This kind of conversation will start making your brain move into parasympathetic mode and will cause increased stimulation from your vagus nerve. In turn, when your vagus nerve sends secretion or sends stimulations to your stomach, the gastrin hormone will be released. Do you recall what type of cell releases gastrin from the stomach gastric pits? That would be an enteroendocrine cell. Okay, so on your worksheet there is a blank. It is for the word vagus. Vagus nerve stimulates stomach glands. We then move to the gastric phase, which is otherwise the stomach phase. At this point, we would consider that a person is eating. So when you're eating and swallowing food, digestion is going to be putting the food into your stomach, the walls of the stomach stretch, and now is when we really need gastrin to release hydrochloric acid from those parietal cells, intrinsic factor, and we need the pH in the stomach to be low, around 1 or 2. Do you know why it is important for us to have a very low acidic environment in the stomach during food digestion? That helps us break down proteins. So what are the 2 enzymes that help break down proteins? They are renin and pepsin. And which one of those specifically is for milk proteins? That is renin. Okay, so if you have an alkaline or a basic pH in the stomach or things of that sort, then that will not work very well for protein digestion. So if you think about people that take like an acid inhibitor or a proton pump inhibitor, there's things like Nexium, for instance, then maybe they have a more difficult time breaking down those proteins. Got to have that acid pH in the stomach for that to begin. So take a look at this picture down below. You'll notice that the reflexes in the stomach are pushing the food down toward this region, and do you recall the name of that region of the stomach? Okay, that's that pylorus region down here at the end of the stomach. All right, so we then move into the third and final phase. This one is called the intestinal phase. And during this phase, there's a reflex called the enterogastric reflex. Technically, enterogastric means intestinal stomach reflex. All right, so at this point, you'll notice that food is coming into the duodenum or duodenum of the small intestine. Interesting, look at these arrows here that are pushing back toward the stomach, back toward the stomach. So in fact, the reflex here slows the emptying of the stomach and forces the stomach to continue digesting, churning, mixing with enzymes, all that food that we now call chyme. By the way, it's spelled like chime, but it's called chyme, and that's that acidic food that's been churned and ground up in your stomach into little square substances. So this reflex here is to prevent food from emptying too quickly into the small intestine. You know, if your stomach can hold a gallon of food, look at the diameter of your small intestine. Your intestine cannot handle that much food coming at once. So we want to make sure that only small bits of food come into the small intestine. So this reflex here slows down the emptying of the stomach. You'll also notice down here at the very bottom, there's some hormones that help to slow the emptying of the stomach. One called secretin, another one we've already talked about called gastric inhibitory peptide, or GIP, and another new one for us here. This one's cholecystokinin. It's called CCK for short. So these hormones here will actually slow the emptying of the stomach. All right, so we're down to the portion on page 87 of your course pack talking about gastric motility and emptying of the stomach. You'll notice here that the way the stomach is positioned, we're actually putting that food down here toward the pyloric region. The most gastric glands are in that pyloric region of the stomach. And again, we want to give the stomach ample time to churn the food into smaller pieces and to mix it with acids and enzymes like pepsin and renin. I want to draw your attention to this link down at the very bottom. I can't play this through my PowerPoint slideshow, but you can look at it. It's a great video showing waves of peristalsis in the stomach. If you've ever heard your stomach growl, you've experienced those waves of peristalsis. And hey, in fact, when you have a stomach growling, it's the air being pummeled toward and into that duodenum. If you can burp and get that air out, then your stomach noises go away. But you're experiencing air being pushed into that small intestine tube when you have your stomach growl. So we empty about 3 milliliters of chyme from the stomach to the small intestine at a time. That's a very small amount, less than a teaspoon or so of fluids and food going into the small intestine. Well, that's why it takes 4 to 6 hours to empty the stomach after a meal. The stomach emptying depends on how much pushback we're getting from the duodenum or duodenum. It also depends on your stomach's activities and the type of meal that you've had. So be sure on your worksheet to fill in this blank. 4 to 6 hours is the time it takes normally to empty a meal. And the next blank to fill in is what types of meals will slow the emptying of the stomach. Well, if you have a fatty meal, a protein-rich meal, or a large meal, all three of those things will slow the emptying of the stomach. So if you think about, if here's your stomach, if you have the pyloric region down here, and this is the body, if you've got a full stomach, the fat actually floats on the top of a fatty meal. And so that is hard to break down. It becomes one of the last things to leave the stomach. That's why a fat meal is oftentimes satisfying. Proteins are also difficult to break down. It does require an acid environment, pepsin and renin. So proteins can slow the emptying of your stomach. That's why eating a protein-rich meal will hold you longer. If you eat an egg for breakfast, for instance, instead of, say, cereal, you may be able to last longer with less calories. And of course, large meals are going to be something that your stomach has to break down over time. So a big meal, fatty meal, protein-rich meal is going to be the one that holds you the longest. Just wanted to end this page with a little discussion of some stomach disorders. Gastritis is a generic term that means inflammation of the stomach lining. It could refer to anything from a viral infection, bacterial infection, or food poisoning. We may not often know the underlying reason for irritated stomach, maybe vomiting, so we just simply say that we've got gastritis. Used to, we would recommend the brat diet, which is bananas, rice, applesauce, and toast, as a way to calm a upset stomach, but they say it's no longer recommended. In fact, that's come out recently because this is a low nutrition diet, not necessarily a good diet for kids. Here is one thing that holds true though. If you've had an upset stomach, perhaps with vomiting and or diarrhea, avoid having milk products because they can increase mucus production and prolong the inflammation to your stomach's lining. So that goes for having a cold or having a stomach ache. Stay away from those milk-based products until you have no more stomach ache or infection. Just wanted to mention gastric bypass surgery. You'll notice here a very tiny pouch is cut off. The rest of the stomach is left in place, still anchored to a piece of the small intestine, but that's a good deal of the stomach that has now been bypassed. So what kinds of problems do you think might arise for a patient who has had gastric bypass surgery? So let's see, we would have less intrinsic factor. What would that lead to? That would cause pernicious anemia, so there's a need for taking B12, right? All right, we would have decreased ability to digest all food groups, especially we would be deficient in digesting our proteins. Okay, what else might you see being a problem for gastric bypass surgery? Well, let's add on there all food groups would be less digested. Okay, so you also notice that there's a piece of the small intestine from here to about here that's been cut off, and the stomach is reconnected. So that means that the stomach will still secrete fluids. They'll still be dumped here into the small intestine, but of course the stomach receives no food. I have heard of cases where people talk about their stomach growling for weeks after the bypass until it eventually gets the hint that nothing's coming to it. Another common form of weight loss surgery is gastric sleeve. Notice here a good portion of the stomach is removed. And yet another one is called lap band surgery. It's basically a little belt that goes around the stomach and controls how much food can go in there. The goal of all three of these surgeries is weight loss, which may be necessary for someone who is at high risk for, say, diabetes mellitus, heart disease, things of that sort. Years ago, people thought that ulcers were stress-related and had no idea that there was an underlying bacterial cause. Nowadays, we know that Helicobacter pylori, or H. pylori, is oftentimes the cause for stomach ulcers. This particular bacterium is quite common. About 70% of the population carries it and doesn't have any problem with it. In fact, it's so common you can pick it up from drinking from a water fountain. Now, if you do happen to have a Helicobacter pylori infection, you'll notice that it can cause bleeding, and of course that introduces acid into the stomach lining. This can also cause terrible stomach aches and can be diagnosed by a simple blood test, nothing more than a prick of the finger. And here's a look at a stomach ulcer. It kind of looks like a canker sore, but that's in the lining of the rugae. All right, so that concludes page 87. Pick me up for the next video. We'll start page 88.